So Vesto Slipher went through and used a telescope to be the first person to take spectra of these galaxies, or nebulae as he knew them. So this is what he saw.
This is actually a spectrum of a star like our own sun. And you can see it's got absorption lines, different elements. There's hydrogen, magnesium, sodium, calcium, and so on. But if you go to the next slide, we'll see here's a spectrum of a star, and now here is a spectrum, Slipher measured, of a galaxy.
Aha, and it looks almost exactly like the spectrum of the star, like it's made of the same stuff, with that one critical difference that it's stretched redward. And Paul, you told us why a spectrum might be stretched redward.
So this shift to the red is called redshift, and we talked about the Doppler effect, and the idea was that if something is moved to longer wavelengths, that's because it's moving away from us. Slipher knew this, and he tried to calculate how fast it was going by looking, for example, this line here seems to match that one over there. So you can look at the shift in wavelengths, use the equations we talked about, and you get a totally ridiculous speed. You get that these galaxies are moving away from us at speeds of hundreds to thousands of kilometers per second. Not kilometers per hour, kilometers per second.
1,000 kilometers per second. That means you can go around the Earth in less than a minute. That is really fast. So, what do we think this means?
Everything seems to be going away from us. I mean, there are a handful of galaxies coming towards us, but by and large, every galaxy is going away from us. What, do we smell bad?
Yeah, it seems to indicate we're a special place in the universe, and this really bothers me because, of course, Copernicus is the person who said we shouldn't think of ourselves as a special place in the universe. Maybe it's better to think of us as just a perfectly average place in the universe, and this seems to indicate that we're like the center of the universe or something.
Yeah, the unpleasant center of the universe. I mean, people have always through history liked to think that the Earth is something special every time it's been proven wrong, and now finally we're getting data that says we are special in the sense we're the worst place in the universe. Everyone else is trying to go somewhere else.
So we were able to make progress on this, and that progress was made by none other than Edwin Hubble. Now, Edwin Hubble had access to the largest telescope on the planet back in the 1915-1920 period. And so what he was able to do was to look at Slipher's nebulae, and when he looked at them with this big telescope, he could see they were composed of stars. So Hubble realized that nebulae were galaxies as we appreciate them today, collections of stars. Now we also were able to go through and calculate how bright a star appears given its distance. And Hubble knew that, and he could go through and therefore compare how bright stars would be in one galaxy and compare them to how bright stars are in another galaxy.
He was making the assumption that the brighter stars in each galaxy would be about the same brightness.
So if they were the same brightness, and I measured how bright it was in this galaxy and this galaxy, I would then know that the ratio of their distances would be equal to the square root of the ratio of how bright their stars appeared or their fluxes. So Hubble did this for a bunch of Slipher's galaxies, and in 1929 he showed the world his result.
Arguably the most important graph ever plotted. The Hubble Law.
Yes, okay. Big statement, Paul.
Of course, I have big statements of speciality.
So let's see. What we've got plotted here are brighter stars. So these are nearby things. Fainter stars, far away things. These things are moving quickly away from us as measured from the Doppler shift. Mm-hmm. These are not measuring quickly at all. And there's this funny relationship that the further away you are, the faster you're moving.
It's not a very tight relationship. The things don't all sit on the graph. Your high school physics teacher would probably mark you down for this one in a lab project. But then, of course, he was measuring distances was very difficult. And in fact, his assumption that the brighter stars in every galaxy are the same was not that good an assumption. Not too bad.
But when you went through and measured the velocity from spectra, that's pretty accurate.
Yeah, Slipher's measurements here are very accurate. So actually, even if the distances are out by you quite a lot, this correlation doesn't go away. And in fact, modern data has confirmed it out to much greater distances.
That's right. So here is, for example, a modern version of Hubble's diagram that plots the brightest stars in galaxies that we know of today called supernovae. These are exploding stars. They're 5 billion times brighter than our sun. And so this diagram, you can see, we see this relationship Hubble saw more clearly, and we could take it out to much larger distances or velocities. This is all the way out to 30,000 kilometers per second. That's 10% of the speed of light.
So just have to think how weird this is. What this is telling us is that every other galaxy in the universe pretty much is moving away from us. And their speeds can be absolutely staggering. But how fast they're going away doesn't depend, for example, on what sort of galaxy. It doesn't matter if you're a big galaxy or a small galaxy. All it seems to depend on is how far it is away from us. So somehow our position is fundamental. Things close to us are only moving away at a slow 100 kilometers a second or so. Only an astronomer would call 100 kilometers a second slow. And the further away it is, the faster it's going. I mean, that's weird. That's really weird.
So there's a puzzle that's really meant to be solved here. And it would be really good to come up with a solution which didn't mean we were the center of the universe.
Okay. Well, in the next video, we'll talk about some possible solutions, some possible explanations for this utterly remarkable graph.